Welcome to our lesson on relationships. We're into our last little section and we're going to look at some interesting relationships now. And so ones that we haven't looked at before. We've been focusing on directly proportional relationships, the directly proportional relationship and the inversely proportional relationship, and see how the graphs and the equations work together. Now we're going to look at the squared relationship and also look at how the equations and graphs link together. And you know what? There's no new tricks here. It's just the same sort of thing as we've done before. But let's have a look. And so here we go. Here is an equation of power, the relationship of power related to current, I, the current in a circuit, and R, the resistance. And as you can see, R is constant. So in effect, what we've got P as the dependent variable. So that's the dependent variable, and the current is the independent variable. Now, if we just look at that, it's in the form of y equals mx plus c, and c is 0. There's no constant there. There's a 0 added. So we can say that P is equal to R times I squared. And as a result of that, we can say P is directly proportional to I squared. The R being the constant would represent the gradient. Okay. Now, if we were to look at the graph from the data, we might be tempted to say, so what's the relationship between P and I? And if we did that, we'd get this sort of graph. P against I, where I is the independent, because it's on the horizontal, and P is the dependent, it's on the vertical. Even though R, it looks a bit like a parabola, but we can never really tell. It's in the form of y equals ax squared. So it looks a bit like a parabola, but we can't be sure because curves are funny. Never worry too much about curves. What you want to look for is a straight line. So how are we going to change it to confirm our prediction? Well, we're going to plot the graph not of P against I, but notice we're plotting against I squared. So because we've got P as the dependent variable, we're making I squared the independent variable, and now the line will be a straight line. And the gradient here will be the change in power over the change in current squared. That's going to be your constant, and that constant is going to be equal to R. And so it's a really nice thing to see that similarly to the way we dealt with the inversely proportional relationship, where we looked at a 1 over the variable, we're looking at a squared relationship here. And if we take the variable and square it and compare it to the dependent variable, we'll get a straight line. And that's how we can show that they're related in the equation like we've seen over there. So the equation predicts for us what is the independent, the dependent, and what's the constant. I hope you've got that. But let's just have a look at a little bit more interesting one that's a little bit more involved. Now, this is known as Coulomb's law. And it's something to deal with electrostatics. It tells us about the force between charges and the relationship between the force and the distance between the charges. So we need to make very clear that this equation is quite complex and it can tell us more than one sort of relationship. But from what we've seen previously, I think we can break them down and try to see what the equation is telling us. And so the first thing that I'm going to do is I'm going to split out those two and say, let's make them a variable. Let's make those in fact, the independent variable. So it's the product of the charges. And we're going to say force here is the dependent variable. Then notice this would be representing the gradient. K divided by r squared, if K and R are the constants. So what do you predict? Well, if we draw a graph of Q1 times Q2 and put the values of that on the horizontal axis and put the vertical axis as the force, then what are we going to get? Well, you've got it. It's a straight line. The force in newtons, Q1 times Q2, Coulomb squared, straight line that passes through the origin, we can say that force is directly proportional to Q1, Q2. And what does this gradient represent? Yes, it's the change in force divided by the change in the product of charge, but it's actually equal to K over R squared. So it's the universal field constant, or the electric field constant, divided by R squared. Okay, so very important for us to see that particular relationship there. Now, let's have a look and let's separate out. And if we were doing a relationship now and said, well, let R be the independent variable. So let R be the independent variable. This is the dependent variable. Let's make that the constant. So K, Q1, Q2 are constant. What sort of graph do you think we will look at now? What sort of a relationship can we start to see? Well, you will see that when you've got the things in the form of y equals m, which is standing for the constant, x, then we can say y is directly proportional to x, which means that f is directly proportional to 1 over r squared. So I want to take a note of that. F is directly proportional to 1 over r squared. This is no longer a squared relationship. It's known as an inverse square relationship. And so by looking at the graph, we will be able to tell whether it's an inverse square relationship if we plot 1 over r squared against f. And that's exactly what I've done here. And you'll see there I've got meters to the minus 2, 1 over r squared, straight line graph that goes through the origin. We can say that f is directly proportional to 1 over r squared. These other factors, they're constant. So what's the gradient going to be? Oh, you've got it. This gradient here, m, is going to be equal to the constant, which is k, q1, q2. Okay. Excellent. I hope that you've understood that principle. So whenever you look at an equation, you can separate it out and start to define the relationships in words. And so coming back to this one, well, there are two relationships that I can see. I can say f is directly proportional to q1, q2, and I can say f is directly proportional to 1 over r squared. Remember, when we say directly proportional to 1 over r squared in words, we can say that means that f is inversely proportional to r squared. And that's a fantastic discovery. It's an important relationship. Remember what we said when we said inversely proportional. If the one increases, the other decreases by the same proportion. And that's what we're going to see here. But the square plays a little bit of an important factor there. So as the one increases, the other will decrease by 1 over r squared. It's going to change the factor a little bit. But we're not too much worried about that. I just want you to get the relationship. Now, let's have a look at our final equation that we're going to look at. Now, this equation definitely has a dependent variable. We can recognize it's even y. It's on its own. Then we've got something that is looking quite strange, that is on its own, and it's got u and t with it. Then we've got something that says half a, and we were told that a is constant, and we've got a t squared. So this really looks quite a mystery. How are we going to unpack all of this? Well, here's an idea. Can we perhaps switch things around to make them look like a straight line? Can we put them into a format that looks like the equation for a straight line? So that's exactly where I'm going to start. I'm going to say, let's call this my dependent variable. And I'm going to now say, because that's a constant, let me switch that around and say that's half a t squared plus ut. Now, I haven't told you anything about what those letters stand for, and I think that's probably an important thing that I should do at this point. But before we get there, let's just take a note of something. Let's take a note that we've got a constant here. The bit in front of the t squared is a constant. This is a bit on its own. So if we were to write y equals mx plus c, then the c corresponds to the ut, the half a corresponds to the m, and the x corresponds to the t squared. So here we've got a very interesting relationship. Even though we've got t in two parts, we need to understand that we can simplify it a little bit. And to help us, the u there stands for speed. Okay, so the u stands for speed, and the t is for time, and the y stands for distance. And like we've said right in the beginning, when we take speed times time, we get distance. So this factor here represents a distance. And so if we go to our graph, and remember this is a distance as well, then we'll see that y against t, we've got a distance, an initial distance that is put over there. That is representing distance. This represents time. And in this case, what we're saying is it's no longer a constant speed. The speed is changing. Look what's happening. The gradient of this line is changing. So over here, the gradient is not very steep, but here the gradient is steep. That's what happens with the parabola. The gradient is changing. This is an example of a graph where an object is speeding up. It is accelerating. The A stands for acceleration. So very quickly, let's go to our next graph and say, if we were to look at this and say, let that be that's still over there, let's make sure that we're going to plot against t squared now. We've got a constant over here. The gradient is constant. That's going to be our value there. And we can say that the y is directly, no, we can't say directly because it's not going through the origin. So what we've got to do is we've got to make sure that this ut part here, the u has to go to 0. And only then can we say y is directly proportional to t squared. Guys, I think we've more or less covered all the different types of relationships. Let's just do a quick recap. Remember, when you have a directly proportional relationship, it's represented by a straight line that passes through the origin, and we must try and represent it in the equation form of y equals mx. That is the most important thing that you've got. So look at equations and see if you can represent them in this type of form. Thank you so much. I hope you've enjoyed that lesson and you've learned more about relationships that we find in both physics and chemistry. From me, so long, goodbye.